Good wishes, dear students. In today's class, you will learn another new concept under Dalton's law of partial pressure. What does the word partial pressure stands for? That is, if you consider an example of air, as you know, air is made up of different types of gaseous components. For example, hydrogen, nitrogen, oxygen, and so on. So when we say partial pressure, it talks about the amount of pressure contributed by oxygen molecule, the amount of pressure contributed by nitrogen molecule, the amount of pressure contributed by hydrogen molecule, and so on. So the word partial pressure stands for the amount of pressure contributed by individual molecule. Further in it, now when we consider any gaseous mixture, there can be some amount of molecules which do not participate in the reaction. So Dalton's law of partial pressure depends on the non-reacting gaseous mixture. I hope you are understanding the point. In a gaseous mixture, there are different types of molecules. Not all of them participate in the reaction. Some of them do not participate. So this concept is based on non-reacting gaseous mixture. And since they do not react, they behave independently. In short to say, the presence of individual component, that is the non-reacting gaseous mixtures, contributes to the total pressure of the mixture. So further moving on to actual Dalton's law, the total pressure of a mixture of a non-reacting gas is the sum of the partial pressure of the gases present in the mixture. You will understand the law better looking at this example. Consider a container where the volume and the temperature is same, but n1 number of molecules are there. If n1 number of molecules are there, what will be the pressure? Will be P1. As you know, pressure is nothing, the force exerted by the number of molecules towards the wall of the container. Consider another container. There again volume and temperature is same, but here different gas it is. So the N2 stands for number of molecules. So the pressure will be P2, that is the force exerted by the N2 number of molecules towards the wall of the container. Consider a third but a larger container where you are able to mix N1 and N2, meaning these two, the number of gaseous molecules in these two containers. So NT, that is a total number of molecule. In all the three cases, volume is same, temperature is same. But what will be the total number of molecules? When you are mixing these two into this container, total number of molecules will be N1 plus N2. So what will be the force that they exerted? That will be, total pressure is equals to P1 plus P2. So if you understand this concept, you will be able to understand the law exactly. That is the total pressure of a mixture of a non-reacting gases. The condition, as I have written, they should be non-reacting gases where volume is also same, temperature is also same here. The total number of mixture of non-reacting gases is the sum of the partial pressure of the gases present in the mixture. You will understand better with this explanation, where further explanation is given. Partial pressure of a component gas is the pressure that would exert if it were present alone in the same volume and temperature. You needn't break your head with this statement. You only remember this diagram where the two different container with the same volume and temperature, but here one type of gaseous molecule that is represented as a N1. So N1 gives out P1 pressure. N2 gives out P2 pressure. When we mix both of them, we are only mixing, they do not react with one another. That is the conditions here, non-reacting gaseous mixture we are considering. So what becomes the total number of molecules? N1 plus N2. And a total pressure is P1 plus P2. So if this part is confusing, you can omit it here. But this law is a very important one. Based on this diagram, you can remember. The same thing what I have written, if we consider in terms of one more container, third container. So if P1, P2 and P3 are partial pressure of gases in a container with volume, and the total pressure will be, as you have written here, P1 plus P2 plus P3. assuming if this is in terms of normal gases. If for the ideal gas, if we have to consider, what's the formula for the ideal gas? PV is equals to nRT. So in terms of pressure we are talking about. So how can we rearrange the formula? nRT by V. So in terms of P1, the formula will be N1 RT by V. You know that R is a gas constant. Temperature is also a constant in all the three cases. Volume is also constant in all the three cases. So we are writing P1 is equals to N1 RT by V. P2 is equals to NT RT by N2 RT by V. But you understand why are we writing in all the three cases to be equal? Because gas constant is a constant and temperature and volume are same in all the three cases. So finally P total will be all the three equations if we write it together, taking out the common factor is RT by V. So the formula will be P total is equals to N2 plus N1 plus N2 plus N3 into RT by V. That is P total is equals to, now N1 plus N2 plus N3 can be written it as a NT here. N total into RT by V. Mathematically little more if we explain, RT by V can be expressed as, now in terms of comparing it with ideal gas equation, we can write RT by V is equals to P1N1. Just look at it. If I am writing RT by V, this N1 will come to the denominator. P1 by N1 is equals to P2 by N2 is equals to P3 by N3. Or in general, we can also write it Pi by Ni. Therefore, P total is equals to N total. Instead of writing RT by V, we can represent by this term Pi by Ni. So finally, P total is equals to N total Pi by Ni. So here if we have to calculate the Pi partial pressure value, what happens? Rearrange this formula. So Ni comes to the numerator here. Ni, this comes to the denominator. So Pi is equals to Ni by N total into P total. The whole thing can be taken it as an Xi. So Pi is equals to Xi into P total. That is Xi is the mole fraction of the ith component. Finally, in one point, applications of Dalton's law is used to calculate the pressure of a dry vapor collected can be calculated. In terms of equation, pressure of a dry gas collected is equals to P total minus, total pressure minus pressure of the water vapor. Now here water vapor, when we say in terms of aqueous tension, and its values are available for air at various temperatures. Thank you.